Ammonia stress corrosion cracking damage mechanisms as a part of environment-assisted cracking. Description of ammonia stress corrosion cracking damage mechanisms based on API 571. Number A. Aqueous streams containing ammonia may cause stress corrosion cracking or ammonia SCC in some copper alloys. Number B. Carbon steel is susceptible to SCC in anhydrous ammonia. Ammonia stress corrosion cracking or ammonia SCC damage. Introduction. Ammonia stress corrosion cracking is a form of environmentally assisted cracking that occurs in susceptible metals when exposed to ammonia-containing environments under tensile stress. It typically affects metals used in chemical processing, power generation, and other industrial applications where ammonia or related compounds are present. Mechanisms of ammonia stress corrosion cracking damage includes, number 1 is, environment. Presence of ammonia or NH3 or ammonium compounds creates a corrosive environment. High pH conditions, alkaline environment, facilitate ammonia's interaction with metal surfaces. Ammonia can penetrate crevices, weld zones, and deposit areas, creating localized corrosive environments. Number 2 is, susceptible materials includes, number A, commonly affected metals include, carbon steels, low alloy steels, certain austenitic stainless steels less susceptible but possible under specific conditions. Number B of susceptible materials is more resistant materials includes, nickel alloys and some stainless steels with proper alloying elements. Number C, susceptibility factors, high residual or applied tensile stresses, presence of welds or heat-affected zones, microstructural features such as grain boundaries. Number 3 of mechanisms of ammonia stress corrosion cracking damage is cracking process. Number A, cracks initiate at areas of high tensile stress, such as welds, bends, or residual stresses. And microstructural irregularities or corrosion pits act as crack initiation sites. Cracking process. Number B, cracks propagate along grain boundaries, intergranular, or transgranularly, facilitated by chemical attack. Ammonia molecules diffuse into the metal, disrupting passive films and promoting localized corrosion. The combination of mechanical stress and chemical attack leads to crack growth. Number 4, characteristics of ammonia SCC damage, crack morphology, typically, intergranular, along grain boundaries, indicating an intergranular SCC mechanism. Cracks are often thin, brittle, and may have a faceted appearance under microscopic examination. Location of ammonia stress corrosion cracking damage often initiate in weld zones, crevices, or areas with residual stresses. Propagation tends to follow grain boundaries or microstructural features. Number C, signs of ammonia stress corrosion cracking damage, evidence of grain boundary attack with corrosion products, presence of brittle, intergranular cracks, material thinning or localized deformation. Ammonia stress corrosion cracking is a hazardous, environmentally assisted failure mechanism characterized by intergranular or transgranular cracks initiated and propagated under tensile stress in ammonia-containing environments. The damage results from a combination of chemical attack, microstructural vulnerabilities, and mechanical stresses. Prevention involves controlling water chemistry, selecting resistant materials, reducing residual and operational stresses, and implementing routine inspections to detect early signs of cracking. Ammonia stress corrosion cracking based on API 571 will affected materials. Number A, some copper alloys in environments with aqueous ammonia and/or ammonium compounds. And number B, carbon steel in anhydrous ammonia. Here's a detailed explanation of affected materials in ammonia stress corrosion cracking. Ammonia SCC primarily affects certain metals and alloys that are susceptible to chemical attack and stress-induced cracking in ammonia-rich environments. The susceptibility depends on the material's microstructure, composition, and environmental conditions. Materials affected by ammonia stress corrosion cracking. Number 1 is common susceptible materials, includes, number A, carbon steels. Widely used in piping, tanks, and structural components, composed mainly of iron with a carbon content typically below 0.3%. Carbon steel's susceptibility includes, highly susceptible to ammonia SCC, especially under tensile stress. Cracks often initiate at welds, heat-affected zones, or residual stress areas. Microstructural features like coarse grains or impurities can exacerbate susceptibility. Carbon steel's damage mechanisms includes, ammonia penetrates grain boundaries, leading to intergranular attack under stress. The passive film on steel can be disrupted by ammonia, promoting localized corrosion. Number B of common susceptible materials is low-alloy steels, for examples, chrome moly steels, such as 2.25 Cr, 1Mo, 3 Cr, 1Mo. The susceptibility of low-alloy steels includes, similar to carbon steels, but alloying elements may slightly modify resistance, generally more resistant than plain carbon steels but still vulnerable under high stress or ammonia concentrations. Number C of common susceptible materials is austenitic stainless steels, for examples, types 304, 316, 321, 347. The susceptibility of austenitic stainless steels includes, it less susceptible than plain carbon steels. However, under certain conditions, high ammonia concentration, elevated temperature, or residual stresses, susceptible to ammonia SCC. Austenitic stainless steel's microstructural factors includes, sensitization, chromium carbide precipitation at grain boundaries, can increase susceptibility. Microstructural variations, such as grain boundary chromium depletion, can facilitate intergranular cracking. Number D of common susceptible materials is nickel and nickel alloys, for examples, Inconel series such as Inconel 600, 625. Resistance of nickel and nickel alloys includes, generally resistant to ammonia SCC. The presence of nickel enhances corrosion resistance, suitable for environments with high ammonia concentrations. Material microstructure and composition influences may be affected by ammonia stress corrosion cracking, includes, number A, grain size. Fine-grained microstructures tend to be more resistant. Coarse grains can facilitate crack initiation and propagation along grain boundaries. Number B, heat treatment state. Properly heat-treated materials with minimal residual stresses are less susceptible. Microstructural features like carbide precipitates can influence susceptibility. Number C, impurities and microstructural defects. Impurities such as sulfur, phosphorus, or segregation at grain boundaries can weaken the material. Microvoids or inclusions act as initiation sites. Environmental factors affecting material susceptibility. Environmental factors like ammonia concentration, temperature, and pH influence the level of susceptibility of these materials. Summary table, materials susceptible to ammonia SCC. Number 1 is carbon steel. It has high susceptibility. Carbon steel is very vulnerable, especially under stress. In high ammonia environments, it corrodes rapidly. Its implication is avoid using carbon steel in such conditions unless fully protected. Number 2 is low alloy steels. It has moderate to high susceptibility. The susceptibility increases at welds and heat-affected zones. These areas are stress concentrators, making them weak points. Its implication requires strict welding quality control and inspection. Number 3 is austenitic stainless steels. It has moderate susceptibility. Generally better than carbon steel, but not immune. Vulnerable when sensitized, such as improper heat treatment. Implication, ensure proper fabrication and stress relief practices. Number 4 is nickel alloys. It has low susceptibility. Excellent resistance in harsh environments. Preferred for severe ammonia or corrosive service. Its implication, higher cost, but long-term reliability. Number 5 is other alloys, such as Monel, Inconel. It has low to moderate susceptibility. Good resistance, but performance depends on specific alloy and environment. Some alloys handle chlorides or ammonia better than others. Its implication, material selection should be based on detailed process conditions. Material selection is critical for components exposed to ammonia environments. Use of nickel-based alloys or specialized corrosion-resistant steels can significantly reduce susceptibility. Proper heat treatment, stress relief, and weld procedures help mitigate risks. Regular inspection and monitoring are essential for early detection of ammonia SCC in vulnerable materials. Critical factors. Number 4 is microstructure and material properties, includes, number A, grain size and boundaries. Coarse grains and certain grain boundary characteristics influence susceptibility. Microstructural features like segregations or carbide precipitates at grain boundaries can weaken the boundary. facilitating intergranular cracking. Number B, microstructural defects. Inclusions, microvoids, or microcracks act as initiation sites. Number 5, oxygen is necessary, but trace amounts are sufficient. Number 6, pH above 8.5. Number 7, occurs at any temperature. Number 8, residual stresses from fabrication or tube rolling are sufficient to promote cracking. Number B, for steel, includes, number 1, anhydrous ammonia with less than 0.2% water may cause cracking in carbon steel. Number 2, cracking has been reported as low as -27 degrees Fahrenheit or -33 degrees Celsius in laboratory testing. Crack growth rates and cracking susceptibility with increasing temperature and can occur at ambient or refrigerated conditions. Number 3, PWHT eliminates susceptibility of most common steels less than 70 ksi tensile strength. Number 4, contamination with air or oxygen increases tendency toward cracking. Number 5, high residual stresses from fabrication and welding increase susceptibility. Here's a comprehensive and detailed explanation of the critical factors that influence ammonia stress corrosion cracking damage. Ammonia SCC is a complex failure mechanism driven by a combination of environmental, material, and mechanical factors. The interplay of these factors determines the likelihood, initiation, and propagation of cracks. Understanding these critical factors is essential for prevention and mitigation. Critical factors influencing ammonia stress corrosion cracking or ammonia SCC includes, number 1, ammonia concentration and composition, includes, number A, ammonia content. High ammonia levels increase the aggressiveness of the environment. Ammonia molecules readily penetrate protective oxide films, disrupting passivity. Elevated ammonia concentrations, greater than several ppm, significantly raise the risk of SCC initiation and growth. Number B, ammonium salts and complexing agents. Presence of ammonium salts or other chemicals can alter pH and corrosivity. Complexing agents may facilitate ammonia's penetration or destabilize protective films. Critical factors. Number 2 is temperature, includes, number A, elevated temperatures. Increased temperature accelerates chemical reactions, diffusion of ammonia into metal, and crack propagation. Typically, ammonia SCC occurs above 50 degrees Celsius or 122 degrees Fahrenheit, with higher temperatures or greater than 100 degrees Celsius intensifying susceptibility. Temperature influences both the rate of chemical attack and the material's mechanical properties. Number B, thermal cycling. Fluctuations in temperature can induce thermal stresses, exacerbating crack initiation. Critical factors. Number 3 is mechanical stress, include, number A, tensile stress. Applied tensile stresses exceeding the material's yield strength or residual stresses from fabrication are critical. Even low levels of tensile stress can initiate cracks if environment and microstructure are conducive. Stress concentrations at welds, corrosion pits, or geometric discontinuities greatly increase local stress intensity. Number B, residual stresses. Residual stresses from welding, machining, or fabrication processes contribute to the overall stress environment. Number C, cyclic or dynamic loading. Fatigue loading can promote crack initiation and growth under ammonia SCC conditions. Critical factors. Number 4 is microstructure and material properties, includes, number A, grain size and boundaries. Coarse grains and certain grain boundary characteristics influence susceptibility. Microstructural features like segregations or carbide precipitates at grain boundaries can weaken the boundary, facilitating intergranular cracking. Number B, microstructural defects. Inclusions, microvoids, or microcracks act as initiation sites. Number C, material composition. Materials with certain alloying elements, such as high carbon, sensitization in stainless steels, are more vulnerable. Nickel alloys and austenitic stainless steels with proper microstructure are more resistant. Critical factors. Number 5 is environment and water chemistry, includes, number A, pH levels. Ammonia environments are typically alkaline, pH greater than 8, which can destabilize passive films. High pH environments favor ammonia SCC. Number B, presence of oxygen or other gases. Oxygen can influence corrosion processes, but in ammonia SCC, the environment is often low in oxygen. The absence of oxygen may promote more localized, intergranular attack. Number C. Deposits and crevices. Deposits or crevices trap ammonia, creating localized aggressive conditions. These microenvironments elevate the risk of crack initiation. Critical factors. Number 6 is environmental and operational conditions, includes, number A, duration of exposure. Longer exposure times increase the likelihood of crack initiation and propagation. Number B, water chemistry control. Proper control of ammonia concentration, pH, and temperature reduces risk. Number C, system design. Avoidance of tight bends, welds, or residual stress zones minimizes stress concentrations and microstructural irregularities. Number 7 is additional critical factors influencing ammonia stress corrosion cracking, includes, number A, weld quality and residual stresses. Poor welds with high residual stresses are more prone to SCC initiation. Number B, surface conditions. Surface roughness, corrosion pits, or deposits increase initiation sites. Number C, microbial activity. Certain microbes can influence ammonia levels or local chemistry, indirectly affecting SCC susceptibility. The critical factors for ammonia SCC damage are interconnected, their combined effects determine the likelihood and severity of cracking. Controlling ammonia levels, managing stresses, selecting resistant materials, and maintaining proper system design are essential strategies to mitigate the risk of ammonia SCC. Ammonia stress corrosion cracking damage affected units or equipment based on API 571, number A, copper zinc alloy tubes in heat exchangers. Number B, ammonia is present as a process contaminant in some services or may be intentionally added as an acid neutralizer. Number C, carbon steel is used for ammonia storage tanks, piping and equipment in ammonia refrigeration units as well as some lube oil refining processes. Here's a detailed explanation of the affected units or equipment that are susceptible to ammonia stress corrosion cracking damage. Ammonia SCC can occur in various units and equipment within industries where ammonia is used, processed, or stored. The susceptibility depends on the operational environment, material selection, and design features. Affected units and equipment in ammonia stress corrosion cracking includes, number 1 is piping systems, includes, number A, ammonia supply and distribution lines are the piping that transports ammonia from storage to process units. The vulnerabilities of this ammonia distribution lines includes stress concentration points at elbows, T's, or welds. Microstructural irregularities or residual stresses from fabrication. The impact of this ammonia distribution lines would be cracks initiating and propagating along the pipe walls, potentially leading to leaks or catastrophic failure. Piping systems. Number B is process piping. This is the piping involved in reactor feed, process loops, or heat exchangers. The vulnerabilities of this process piping includes elevated temperatures and ammonia concentrations, cyclic stresses from thermal expansion. The impact of this process piping would be localized cracking, especially near welds or bends. Number 2 of affected units and equipment in ammonia stress corrosion cracking is storage tanks and vessels, includes, number A, ammonia storage tanks. Large pressure or atmospheric tanks storing ammonia. The vulnerabilities of this ammonia storage tanks includes residual stresses from fabrication or operation, corrosion at weld seams or fittings. The impact of this ammonia storage tanks would be intergranular cracks or through-wall cracks leading to leaks or rupture. Number B, reactor vessels. It's using ammonia in chemical processes. The vulnerabilities of this reactor vessels includes high internal stresses during operation, microstructural conditions favoring SCC. The impact of this reactor vessels would be cracks affecting structural integrity and process safety. Number 3 of affected units and equipment in ammonia stress corrosion cracking is shell and tube heat exchangers. This equipment transferring heat between ammonia and other process streams. The vulnerabilities of this shell and tube heat exchangers includes stress from thermal cycling, localized corrosion in crevices. The impact of this shell and tube heat exchangers would be crack initiation at welds or tube attachments, risking leaks. Number 4 of affected units and equipment in ammonia stress corrosion cracking is valves and fittings. This valves controlling ammonia flow, pressure-reducing devices, and fittings. The vulnerabilities of this valves and fittings includes stress concentrations due to design features, microstructural irregularities from manufacturing. The impact of this valves and fittings would be cracks propagating from stress points, leading to leaks or failures. Number 5 of affected units and equipment in ammonia stress corrosion cracking is pump and compressor components. This mechanical component circulating ammonia under pressure. The vulnerabilities of this pump and compressor components includes vibrations and cyclic stresses, residual stresses from manufacturing. The impact of this pump and compressor components would be crack initiation in casings, shafts, or seals, risking operational failure. Number 6 of affected units and equipment in ammonia stress corrosion cracking is heat transfer surfaces and linings. This surfaces in contact with ammonia, such as in scrubbers or absorbers. The vulnerabilities of this heat transfer surfaces and linings includes surface corrosion due to ammonia exposure, microcracks from thermal or mechanical stresses. The impact of this heat transfer surfaces and linings would be progressive cracking leading to leaks or equipment failure. Number 7 of affected units and equipment in ammonia stress corrosion cracking is structural supports and foundations. This supports structures for piping, vessels, or tanks. The vulnerabilities of this structural supports and foundations includes residual stresses or deformation, corrosion at contact points. The impact of this structural supports and foundations would be structural failure affecting entire systems. Key points: welded joints and stress concentration zones are common sites for ammonia SCC initiation. High temperature zones and areas with residual stresses are particularly vulnerable. Regular inspection, non-destructive testing, NDT, and material monitoring are critical for early detection. Final notes: the affected units and equipment are often integral to ammonia handling and processing systems. Preventive measures include proper material selection, stress relief, weld quality control, and environmental management. Awareness of susceptible equipment enables targeted inspections and maintenance to prevent catastrophic failures. Ammonia stress corrosion cracking appearance or morphology of damage based on API 571, number A, copper alloys, includes, number 1, surface breaking cracks may show bluish corrosion products, number 2, exchanger tubes show single or highly branched cracks on the surface. Number 3, cracking can be either transgranular or intergranular, depending on the environment and stress level. For transgranular, see Figure 4-154 ammonia SCC in an inhibited Admiralty tube UNSC 44300, 0.75 inches. Diameter, BWG 16, 0.063 inches. Thick, with extruded fins. For another transgranular, see Figure 4-155 high magnification view of a cross-section of the tube in Figure 4-154 showing transgranular cracking. Mag. 500X. For intergranular, see Figure 4-156 high magnification view of a cross-section of a brass exchanger tube showing intergranular cracking. Ammonia stress corrosion cracking critical factors based on API 571 number B, for carbon steel, includes, number 1, cracking will occur at exposed non-PWHT welds and heat-affected zones. Number 2, cracking is primarily intergranular in nature. Here's a detailed explanation of the appearance or morphology of ammonia stress corrosion cracking damage. The morphology of ammonia SCC is characterized by specific features that reflect the nature of the crack initiation and propagation mechanisms under the combined effects of chemical environment and mechanical stress. Understanding these features is essential for diagnosing failure modes, assessing damage severity, and implementing appropriate mitigation strategies. Appearance and morphology of ammonia stress corrosion cracking, SCC, damage, includes, number 1 is general morphological features, includes, number A, intergranular versus transgranular nature. For intergranular cracks, cracks that propagate along grain boundaries, common in materials susceptible to intergranular attack due to sensitization or microstructural segregation. Appear as parallel lines or networks following grain boundary paths. For transgranular cracks, cracks that cut through grains, crossing grain boundaries, less common in ammonia SCC but can occur under certain conditions, often appear as rough, jagged cracks traversing grain interiors. General morphological features is crack morphology. For brittle, cleavage-like appearance, cracks often exhibit a brittle fracture morphology, with smooth, flat facets indicative of cleavage or intergranular fracture. The fracture surface may be smooth and shiny, reflecting brittle failure. General morphological features is crack morphology. For brittle, cleavage-like appearance, cracks often exhibit a brittle fracture morphology, with smooth, flat facets indicative of cleavage or intergranular fracture. The fracture surface may be smooth and shiny, reflecting brittle failure. For dimpled or fibrous features, less typical for ammonia SCC, but some ductile tearing features may be observed if localized ductility exists. Appearance and morphology of ammonia stress corrosion cracking damage. Number 2 is surface features of ammonia SCC. Number A, crack initiation sites, usually associated with microstructural irregularities, such as inclusions, carbides, or microvoids. Initiation may occur at corrosion pits or microcracks, often visible as small, localized damage zones. Surface features of ammonia SCC. Number B is propagation features, includes flat, planar fracture surfaces, indicative of intergranular cracking, characterized by a smooth, mirror-like finish along the crack path. For step-like features, when cracks propagate through multiple grain boundaries or along different planes, resulting in step-like or scallop features, and for corrosion products and deposits, ammonia SCC surfaces may show fuzzy or granular corrosion deposits along crack faces due to chemical reactions. These deposits may be ammonium salts or other corrosion products. Appearance and morphology of ammonia stress corrosion cracking damage. Number 3 is microstructural morphology, includes, number A, crack path, often follows grain boundaries, resulting in intergranular crack paths. The crack may branch or bifurcate along different grain boundary planes. Microstructural morphology. Number B, fracture surface, exhibits features characteristic of brittle fracture, faceted appearance with smooth cleavage facets, presence of intergranular cracks with step-like features at grain boundaries. Appearance and morphology of ammonia stress corrosion cracking damage. Number 4 is cross-sectional morphology, includes, number A, crack morphology in cross-section. Cracks are often narrow and deep, with significant aspect ratios. Microvoid coalescence may be observed at the crack tip if ductile rupture features are present. Cross-sectional morphology. Number B is corrosion-related features. Microvoids and corrosion pits may be observed near crack origins. Localized corrosion can be evident along grain boundaries or at inclusions. The morphology of ammonia SCC damage is often intergranular and brittle, with smooth, planar fracture surfaces that follow grain boundaries. The presence of corrosion deposits and microstructural irregularities can help identify SCC damage versus other failure modes like ductile overload. Ammonia stress corrosion cracking damage prevention and mitigation based on API 571, number A, copper alloys, includes, number 1, copper-zinc alloys show improved resistance as zinc content decreases below 15%. Number 2, the 90-10 Cuny and 70-30 Cuny alloys are nearly immune. Number 3, SCC in steam service can sometimes be controlled by preventing the ingress of air. Number 4, 300 series SS and nickel-base alloys are immune. Number A, carbon steel. Number 1, SCC of steel can be prevented through the addition of small quantities of water to the ammonia, 0.2% minimum. Consideration must be given to vapor spaces could have less than 0.2% water present due to partitioning of ammonia in water phase. Number 2, an effective PWHT of the vessel reduces residual stress to the point where ammonia SCC can be prevented. Number 3, low-strength steels, less than 70 ksi tensile strength, should be used. Number 4, weld hardness should not exceed 225 bhn. Number 5, prevent ingress of oxygen into storage facilities. Low levels of oxygen, less than 10 ppm, have been reported to lead to cracking under some conditions. Here's a comprehensive and detailed explanation of prevention and mitigation strategies for ammonia stress corrosion cracking. Preventing ammonia SCC involves controlling environmental, material, operational, and maintenance parameters to reduce the likelihood of crack initiation and propagation. Effective mitigation combines proactive design, material selection, process control, and inspection strategies. Prevention and mitigation of ammonia stress corrosion cracking includes Number 1 is material selection and design considerations, includes, number A, use of corrosion-resistant materials, includes, the first is low susceptibility alloys, select materials with high resistance to intergranular attack, such as, austenitic stainless steels with proper stabilization, for example 304L, 316L, nickel-based alloys, e.g., Inconel, Monel, with excellent corrosion resistance, titanium or zirconium alloys in highly aggressive environments. The second of corrosion-resistant materials is avoid susceptible microstructures, use materials free from sensitization, for example avoid high-carbon steels prone to carbide precipitation at grain boundaries. Material selection and design considerations. Number B is proper material design, includes, the first is welded joints, use weld materials compatible with base metals and resistant to SCC, apply controlled welding procedures to minimize residual stresses. The second is designed for stress reduction, avoid sharp corners, abrupt changes in cross-section, and stress concentration features. Incorporate generous bends and smooth transitions. Prevention and mitigation of ammonia stress corrosion cracking. Number 2 is environmental control, includes, number A, ammonia concentration management, maintain controlled ammonia levels, avoid excessive ammonia concentrations that promote corrosivity, use process controls to keep ammonia within specified safe limits. Environmental control. Number B is pH and temperature control, includes, the first is maintain optimal pH levels, keep the environment within a pH range that minimizes susceptibility, typically neutral to slightly alkaline, and the second is temperature control, operate at temperatures that do not favor SCC, avoid high temperature excursions. Environmental control. Number C is inhibition and additives or commonly using corrosion inhibitors, use chemical inhibitors compatible with ammonia systems to reduce corrosivity. Regularly monitor inhibitor effectiveness. And number D is controlling microbial activity using biocide treatment, prevent microbiologically influenced corrosion that may exacerbate SCC. Prevention and mitigation of ammonia stress corrosion cracking. Number 3 is operational practices, includes, number A, stress management. Reduce mechanical stresses by implement proper stress relief procedures post-welding or fabrication. And minimize residual stresses through heat treatment or stress relief annealing. The second is manage operational stress control, avoid overpressurization. Operate within the elastic limits of equipment. Number B of operational practices is thermal cycling and temperature control. Avoid rapid temperature changes, prevent thermal shocks that induce cyclic stresses, maintain stable operating temperatures. Operational practices. Number C is maintenance and inspection, includes, the first is regular inspection, use non-destructive testing, NDT, methods like ultrasonic testing, radiography, or dye penetrant to detect early cracks. The second is leak monitoring, install sensors and leak detection systems to identify cracks early. Prevention and mitigation of ammonia stress corrosion cracking. Number 4 is protective coatings and barriers, includes, number A, application of coatings, use corrosion-resistant coatings or linings on internal surfaces to prevent contact with ammonia. Number B, cathodic protection, implement cathodic protection systems where applicable, especially in storage tanks and piping. Prevention and mitigation of ammonia stress corrosion cracking. Number 5 is process and system design improvements, includes, number A, stress reduction via design systems to minimize residual and operational stresses, use finite element analysis to identify and alleviate stress concentration zones. Number B, system redundancy and fail-safe features. Incorporate safety features such as pressure relief devices, designed for ease of inspection and maintenance access. Prevention and mitigation of ammonia stress corrosion cracking. Number 6 is monitoring and early detection, includes, number A, corrosion monitoring. Use corrosion coupons, sensors, or electrochemical techniques. Regularly analyze corrosion products for early warning signs. Number B, crack detection. Employ advanced NDT methods such as acoustic emission testing or phased array ultrasonic testing. And number C, material condition monitoring. Perform periodic metallurgical examinations to assess microstructural integrity. Prevention and mitigation of ammonia SCC require a comprehensive approach combining material science, engineering design, process control, and maintenance. Regular inspection, proper material choice, operational discipline, and environmental control are critical to avoiding catastrophic failures associated with ammonia SCC. Ammonia stress corrosion cracking damage inspection and monitoring based on API 571, Number A, for copper alloys. Number 1, monitor pH and ammonia of water draw samples to assess susceptibility of copper alloys. Number 2, inspect heat exchanger tubes for cracking using EC or visual inspection. Rolled area is highly susceptible. Number B, for steel storage tanks and or piping in anhydrous ammonia. Number 1, WFMT welds inside tanks. Number 2, external UT shear wave inspection using TOFD. Number 3, AET. Here's a detailed explanation of inspection and monitoring methods used to detect ammonia stress corrosion cracking damage. Detecting ammonia SCC early is critical to prevent catastrophic failure. Because SCC often initiates internally or along grain boundaries, specialized non-destructive testing, NDT, and monitoring techniques are employed. These methods aim to identify crack initiation, growth, or corrosion-related features before failure occurs. Inspection and monitoring methods for detecting ammonia stress corrosion cracking, SCC, damage. Number 1 is visual inspection. It is purposed to detect surface indications of cracking, corrosion products, or leaks. And most effective in accessible areas, visual inspection commonly applied to inspection of external surfaces for discoloration, corrosion deposits, or deformation. Its use of magnifying lenses or borescopes for detailed examination. Visual inspection limitations are, cannot detect subsurface or internal cracks, limited to accessible regions. Inspection and monitoring methods. Number 2 is ultrasonic testing or UT. It is purposed to detect internal cracks, especially intergranular SCC. It measures crack size and depth. Ultrasonic testing method include, the first UT method is called pulseco ultrasonics, sends high-frequency sound waves into material, reflections indicate flaws. The second UT method is called phased array ultrasonic testing or PUT, uses multiple elements to steer and focus beams. Capable of producing detailed images of internal flaws. The third UT method is called time-of-flight diffraction or TOFD, detects small cracks by analyzing diffracted signals at crack tips. The third UT method is called time-of-flight diffraction or TOFD, detects small cracks by analyzing diffracted signals at crack tips. Ultrasonic testing or UT application. UT suitable for thick-walled components, pipes, and vessels. UT can perform angle beam or immersion UT depending on geometry. Ultrasonic testing or UT advantages, excellent for internal defect detection. It is quantitative sizing. Limitations of ultrasonic testing or UT, requires skilled operators. Surface roughness can affect signal quality. Number 3 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is radiographic testing or RT. This RT is purposed to visualize internal cracks and flaws through X-ray or gamma-ray imaging. RT is applied to detect discontinuities within welds or bulk materials. RT useful for complex geometries where UT is challenging. Radiographic testing or RT limitations. RT less effective for very small cracks. RT exposure to radiation. Number 4 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is magnetic particle testing, MT, and dye penetrant testing, PT. Number A, magnetic particle testing or MT, MT used for ferromagnetic materials, MT used to detect surface and near-surface flaws. Application of MT involves magnetizing the component and applying magnetic particles to surface. Number B, dye penetrant testing or PT, PT used to detect surface breaking cracks. To perform dye penetrant testing, follow these steps: surface shall be cleaned, dye penetrant is applied, excess removed, then a developer reveals indications. Limitations of dye penetrant testing, only for surface breaking cracks, not effective for internal SCC. Number 5 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is acoustic emission monitoring. It is purposed to detect rapid release of energy from crack growth. It is suitable for continuous or periodic monitoring. Application of acoustic emission monitoring. Sensors placed on equipment surface detect transient elastic waves, capable of identifying active crack growth during operation. The advantages of acoustic emission monitoring are real-time monitoring, sensitive to dynamic cracking events, and the limitations of acoustic emission monitoring are, requires complex data analysis, noise from other sources. Number 6 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is electrochemical inspection techniques. Number A, potential monitoring, includes, measure corrosion potentials to assess corrosion activity. Use of half-cell potentials for localized corrosion detection. Number B, electrochemical impedance spectroscopy. It used to evaluates corrosion rate and film integrity. It is sensitive to changes in corrosion behavior over time. Its application is to detect early signs of localized corrosion that might precede SCC. Number 7 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is advanced and specialized methods, includes, number A, replica techniques. Use of replica films or impression materials to capture surface features. Analyzed under microscopes for crack initiation evidence. Number B, infrared and thermal imaging, detect anomalies in thermal signatures indicating corrosion or cracking. Number C, digital image correlation, DIC strain measurement technique to detect surface deformation indicative of subsurface cracking. Number 8 of inspection and monitoring methods for detecting ammonia stress corrosion cracking damage is monitoring strategies, includes, number A, regular scheduled inspections. Follow industry standards, such as ASME, NACE. Use appropriate methods based on component accessibility and risk. Number B, continuous monitoring. Install sensors, AE, corrosion potential probes, for real-time data, enable early detection of active crack growth. Number C, inspection frequency, increased frequency in high-stress or high-risk areas, use risk-based inspection planning. Multimodal approach, combining several methods increases reliability, risk-based inspection, RBI prioritize high-stress, high-risk areas, regular monitoring. Early detection enables proactive maintenance, documentation trending, track inspection data over time to identify crack growth trends. Thank you.